For the second part of the video, we will take a look at the different types of protein gel lipolysis. So as I was saying earlier on in the first video, so there are 6 kinds of page. So basically, even though you see over here it's 7, okay, IEF is actually just the method, okay, which is a part of the 2D. So we have, okay, the first is native page, second native gradient page, we have urea page, we have SDS page, the most common. We also have SDS gradient page, we have IEF, okay, which is actually the first dimension for the two-dimensional page, and of course we have the two-dimensional page, which is actually the running of the gel after IEF. Alright, so let's have a look at each and every one of them. So for the native page, so protein are usually separates based on charge, size, and shape. So this is again the type of gel. If you were to separate your protein based on charge, then you should use native page. Then you could actually determine the charge. By SDS page, you will not be able to determine the charge. It's only just by the size. Now, native page is actually useful for examining protein-protein or protein-ligand interaction, and also to detect protein isoform or conformers. Okay, so what is isoform or conformers? Okay, we will basically have a look at probably in about 2 weeks time, okay, next week or 2 weeks time, because in protein there are lots of isoforms or protein isomers. Now, for the native page, these are some of the examples, and as you can see, actually not many people like to make the native page because it's actually not easy. Well, I wouldn't say it's not easy, it's just that to make the gel, you need to basically ensure that the condition or the surrounding area is actually cold. So usually it has to be done in a cold room. It has to be in around 4 degree. And later on, again, when running as well, again, it also needs to be in the cool conditions. So it basically needs a bit of extra tender loving care. Alright, so let's have a look at the examples. So on your left over here, okay, which is from a journal in 2003. So there is a video over here if you're interested. Okay, so just copy and paste, okay, and put it in YouTube to be able to view it. So what happens then, okay, as you can see over here, the description: in the absence of phospholipids, both twin filaments run as a single sharp band on this gel. So this the WF1 and 2. So whatever it is, okay, that you see, okay, this one, okay, and this one, okay, they move more rapidly towards the anode, okay, indicating a net increase in the negative charge and thus a binding interaction, which means that they basically, well, if you were to refer, okay, to the paper, so this is actually quite an old paper, about 17 years ago, so they basically wanted to see, okay, the difference, okay, especially between these two isomers. So these are isomers TWF1 and 2, and they basically have been bound, okay, to a substrate, and then they wanted to see how it interacts, okay, or how they are further separated or based on the charges, negative charges explained here. And the other one, again, from even earlier paper, which is on 2000, okay, about 20 years ago, dimerization of Ker-2-TL1, okay, in the presence of carbon dioxide. So as you can see, okay, over here, these are based on the treatments and different levels of carbon dioxide. Sorry, it's actually not carbon dioxide. That's why I actually forgot, because this paper is actually quite old. It's cobalt, okay? So different concentration of cobalt, okay? So basically it has an effect on the protein. So as you can see, okay, so when treated, okay, with cobalt, okay, because this is basically, it has a charge, okay, so the charges has changed from the original, as you can see over here. So the original actually doesn't have, okay, a larger size protein, okay, but okay, when it bound or when it reacts, okay, or interact, okay, with cobalt, so this is what happened. So you can see that, okay, the charges have changes. Now for gradient page, okay, usually a lot of this page, okay, either native or SES, they could be made into a gradient page. What we meant by gradient, okay, and if you understand the word gradient, okay, is that it has a ranges of concentration all in one gel. Because usually when you make a gel, it's just one percentage, right? Either 1%, 3%, okay, 50%, 4%, like in protein and whatnot. But for gradient, okay, you can have a range of concentration. Let's say about 4 to 16%, 5 to 20%, okay, 4 to 7%. Okay, so those are gradient gel. So native gradient gel are made in such a way. So the function is to separate native proteins by size. Okay, so that means that protein stops moving when they reach a certain I forgot the C. Certain gel density, but of course, okay, this may take a very long time. And did you know that actually to run the native gel, it takes a couple of hours longer than SDS page. SDS page could be done in about 45 minutes or 1.5 hours if you want if you want it to be separated smoothly. But usually 45 minutes is enough. So, but over here is, I would say I've never run native page, okay, but I've seen my friends did it. So minimum is about 3 to 4 hours, but usually she would just leave it overnight in the cold room. So as you can see, native gradient page, okay, is a great technique, okay, to study protein oligomerization, especially related to PTM or post-translational modification. Alright, so again, this is one of the examples. Okay, native 4 to 15% gradient page. So you can basically later on see how it separates, okay, on the gel. And usually separation would depends on the range. So then, well, the closer the range is, okay, towards a certain level, okay, let's say towards 0 or towards, okay, the upper part 20 to 30%, usually, okay, it would be better for certain types of protein only, okay, larger or smaller protein, similar to the basic knowledge of concentration versus size. Alright, so the third types of page is urea page, okay, so using urea, so it is done to separate denatured protein by size and charge only. So you don't really care about the size over here, and of course when you run urea page you actually know your protein very well, so it is only done for targeted protein. So usually the concentration of urea to be used is around 6 to 8 molar, which is quite high, and this is actually a great technique to study protein modification. If you are sure that your protein goes through modification and you wanted to see how basically the size or the charges change, okay, through the modification, so it could be done using urea page. And this is also one type of page, okay, that basically you could determine the charge, okay, whether it's positive or negative. Now for urea page, okay, usually it is used for low molecular weight protein or membranous protein. So of course, okay, maximum concentration is 8 molar. Nobody has ever used more than that, because more than 8 molar, usually you basically will damage your protein. So apart from that, okay, urea, okay, so urea usually has to be heated up, okay, so it could denature secondary DNA or RNA structure, okay, from around 2 to 500 bases. So this is an example of urea page, okay, so you can see some dimer form here, okay, monomer, okay, and also monomer, okay, which is basically another monomer. This is actually a mistake over here, okay, so both are monomer, okay, but this is basically a PTM or post-translational modification that occurs to the monomer. Alright, so the next type of page is the most common, okay, and the one that probably will focus a lot is on SES page, okay. So of course there is a link over here. You could just copy paste, okay, to YouTube to view it if you're interested. Again, separation is based on, well, negative to positive only, okay, not so much on the size, but more on charge, but more on the size. So more or less, okay, the ratio size or charge is nearly the same for many SES denatured proteins. So this is one form of denatured protein separation technique. So protein are separated only by the length of the polypeptide chain, but not by the differences in the charge, okay, because it has been denatured. So it is a great separation technique because it allows estimation of the size of the chain of your polypeptide. Now, apart from normal SDS page, we also have SDS gradient page. So similar to the native gradient page, so that means that you have a set of concentration, range of concentration for the SDS gradient page. So for example, over here you have, let's see the difference, okay, between one single concentration versus a range of concentration 12.5, okay, to 5 to 20%. So the difference, okay, is that again, okay, similarly it depends on the ranges, okay, whether it would be useful for larger or smaller proteins, okay. So separation of the protein base, okay, is based on the ranges of concentration. All right, so now, oh, probably it's not really that clear because I was stretching, okay, the picture, okay. So these are types of commercial gels available, whether singly, okay, or in a range or gradient, so you can purchase it. What I did when I was doing my PhD, yes, I did buy it. I did try to make a gradient page, but it doesn't work. Okay, so that's why I bought it. Okay, so basically, okay, you can see the differences. For example, if you have around 15% and you compare it to 4 to 15%, you can see how the marker separates, right? So over here, 250 is a bit above. Okay, over here, the 250 kilodalton is a bit lower, and it is good. Okay, if you want to separate your lower size or basically smaller size protein, okay, this kind of gel, so you can actually see the differences, okay, and make your choice before you make it yourself or before you purchase. Now, let's have a look at the comparison between SES versus the native page, and these are all 1D or one-dimensional page. Okay, so for the 2D, it will be in a separate video. So SES versus native. So this is basically a representation of SES. Okay, so SES is a denatured form of protein. Okay, so usually we add a mercapto ethanol, okay, to the protein, we heat it up, okay, so that, okay, your protein from its tertiary or quaternary structure, it will be more or less denatured, okay, to be in polypeptide chain, and then you just run it on the gel and it will be separated, okay, based on the size, of course, from negative to positive, not so much on the charge, as compared, okay, to the native, okay, over here. So you can have large high positive charge or large, okay, low positive charge, okay, which you could differentiate on the gel all at one go, whereby this is only for the size, this is for size, and also for the charges. So what you can, I actually don't have a side-by-side comparison of SDS and native, okay, in terms of the actual gels. Okay, what I could give you, okay, is actually from some of the marker that has been done. So this is, okay, basically what you see, okay, on a typical SDS page. This is from a native page. They are basically of similar protein, okay, being made into a marker. So the myosin that you see over here and the myosin that you see over here run on the same gel, okay, but you can see that basically the band, okay, is not on par or not parallel one to another. Okay, so the same, okay, with all other, because this is based on the charges as well, not so much on the size, but this is very size dependent. Okay, another one is basically similarly, this is actually native and this is the other way around, this is SDS page. um, I actually could remember the paper is from, I think, below 2010. I think it's 2006, 2007. Okay, but this is actually on liver cell as well. So when they run on the native gel, so and after modification, okay, they can see, okay, that the size is around 15 kilodalton, and based on this, okay, this is actually a low negative charge. But over here, when they run it on SES page, okay, well, they could see that it separates, okay, into many bands, but doesn't tell them of the charge and so forth. Alright, so that would be the end of the 1D gel. Okay, move on to the third video for the a bit lengthy explanation of the 2D gels.